Now, talking about chemical kinetics, we look at the rate factors, which we can identify very quickly with the acronym CANTC, concentration, area, nature, temperature, and catalyst. Well, the one we're working on is rate proportional to function of concentration. And that's trying to generate rate laws. Well, the areas that we need to look at, of course, are rate average, rate proportional to reaction coefficients of the balanced equation, and experimental rate laws. Where we define the rate trends and rate constant. Now, the experimental trends, the orders of reaction can only be determined by experiment. So that's where we are now. And the fourth area that we look into are what we call integrated rate laws. Now, when we talk about integrated rate laws, we're talking about two factors involved in here. That is rate proportional to a function of concentration and time factors. And we call it the decay process. Integrated decay equations, or however you wish to look at it. So when we look at the idea of integrated rate laws, we start with the definition of rate and connect that definition with the empirical rate law, and then set up an integration to determine concentrations against time. Okay, so rate is essentially given as a change in concentration, as you know, over change in time. So what we'll do is assume a simple reaction A goes to products. So then we can write the rate now as a change in concentration of A over change in time, and that is equal to the empirical rate equation, K, times the molar concentration of A, raised to the X power. Now, in the idea of determining what we call an integrated rate law, we have to apply the differential relationship in that. And what that essentially says is that we have to rearrange this expression into an expression that looks like this, change in A over concentration of A raised to the X power, and that's equal to K times the change in temperature, and that's a differential relationship. And when we put it into the integral relationship, is dA over A, like that, raised to the X power, to equal K dt. So we have concentration as a function of time, is what essentially the relationship is telling us. Now, to determine what the expressions are, we simply take the first integral of the expressions given. And so you would start out with a zero order and take the integral of that. Well, that would simply be the integral of dA, which would give you A, and it would give you a constant times A. And that's how it comes out. Now, we can go through each order of reaction like this, 0, 1, and 2. Well, we're only going to concentrate on the first order integrated rate law. So the bottom line is you simply reduce it to this. Now, whether you've had calculus or not doesn't matter, because the outcome of this first order integration is a very, very classic type equation, and that's the only thing you really need to remember is how to work with the equation that comes out of this. Well, this is simply the integral of 1 over A concentration, d concentration of A, to equal K on the integral of dt, which gives us Ln of concentration of A. So that is the integral of 1 over x, if you're looking at it that way, going from A naught to A final. And this is equal to K times T. Now, in the decay expression, we find that the rate constant will be decreasing. It will be a negative value because you're defining the equation in terms of the reactant side. And so when we look at that decay curve, we find the reactant concentrations follow this trend. This is called the first order decay trend. And we'll make that concentration A, and over time, going out that way, like that. So slope in here is decreasing, okay? It's a negative slope, so we have to come in here and we have to install a negative value for that slope, KT. So, and when you work this from initial to final, you have Ln of A final minus Ln of A naught to equal minus KT, and that simplifies to the ratio A naught over A to equal minus KT. And this relationship, being a natural log ratio, becomes, well, A over A final, if you would, to equal e to the minus kt. So that's a base natural logarithm. And then finally, this expression becomes a to equal, it should be a over a naught, didn't it? I don't want a naught on top. No. When we change that to reciprocal, this has to change also. Your a naught and your a, sorry. I always forget that. Sorry. Equals this should be like this. So that should be a equal a naught e to the minus kt, or simply a concentration equals a naught e to the minus kt. So that is the origin of the first order decay. Now I give you this derivation because of its classic nature, and as you go forward in the course and go into higher level courses, you will be expected to know where this comes from. And it's just a matter of integrating the rate relationship. This used to be dA over dt and K times the concentration. And so you rearrange it so that it is as a function of time. And that's the long and the short of it. And then you solve for whatever you apply as an exponent to the rate law. In this case, we applied it to the first order rate law. Well, so we want to derive from the first order decay equation, we want to derive the half-life equation, which will be the second important equation you'll need. Well, half-life, by definition, is the time to reduce initial concentration to 1/2 its value. So if this is the initial concentration, A naught, then half of that would be halfway. About right in here. So that's A naught over 2. And so if we extrapolate to the curve and then down, we have the half-life, the time it takes to reduce the initial concentration to 1/2 its value. This is called the first half-life. Right there, or just T1/2 1. Now, if you cut to the second one, right there, that's 2 half-lives, or A naught over 4. So you're taking half of the next half. And so that's the second half-life. And then, of course, the third half-life, fourth half-life, and so forth. Now, you'll find that one thing that's unique that's not in the first order decay is that all half-life values are the same. It's a constant. So the time 1 for half-life 1 equals time for half-life 2. And that's exclusively for a first-order decay equation. That is, your half-life is a constant. That is, T1/2 1 equals T to 1/2 2, which equals T1/2 3, and so forth. So if you have, say, 10 days for the first half-life, it's going to be 10 days for the second half-life, third half-life, and so forth. So if you wanted to know, say, 50% that's been consumed, and 75% consumed is 10 and 10, 20 days. And so that's just a perspective thing right now. We'll work the problems in a minute on what this means. Okay, now the derivation of the expression for half-life. Okay, the expression for the half-life begins, of course, with kind of an expression. We'll go ahead and redraw the curve. And so this is A naught concentration, and then we'll go say somewhere right in here, I guess, A naught over 2. And so there's your T to the 1/2 right there. Now the equation, or the curve, is defined by A equals A naught E to the minus KT. But what's going to happen is we want to find out what T1/2 is. And so starting with A equals A naught E to the minus 1/2, then A becomes equal to A naught over 2, because that is the first half-life. Right there. So if we take the second part of this expression, A naught E to the minus KT to the 1/2 equals A naught over 2, we see we can divide both sides by A naught. And so we get the expression E to the minus KT to equal 1 over 2, or 1/2. Now you can do anything to a mathematical equation, as you remember from your math teacher, but you got to do it to both sides. So we're going to take the reciprocal of this. And what that gives us is a positive KT equals 2. And then we take the logarithm of both sides, ln of e to the kt, and that's 1/2, forgot that. That should be 1/2, because that's what we're doing, equals ln of 2. And I hate to get it off the page. Ln of 2. Well, this portion right here then becomes just simply kt to the 1/2, like that, and ln of 2 is 0.693. So you have the half-life equation right there, which is in terms of K also, rate constant. It doesn't even have a concentration in it, concentration term. So we can use this expression to solve for the half-life and the K value, the rate constant given the half-life. And so T to the 1/2 now is 0.693 over the rate constant, or 0.693 over the half-life to get the rate constant. So you have two potential calculations there, and in some problems you will have to take a half-life, calculate K, and then calculate something else. 2 steps, you'll see it when we start working through some problems. And this one is the half-life expression given K. So we're looking at two equations now, the KT to the 1/2 0.0693, and then your standard classic first order decay. And that's what we want to show you how to use now in working some decay problems. Okay, SO2Cl2 as a gas, okay, goes to sulfur dioxide as a gas, and chlorine gas. Okay. In an experiment, the initial concentration of sulfuryl chloride, SO2Cl2 initial, is given to be 0.0248. I'll just put molar, mole per liter. If the rate constant, K, for the reaction is 2.2 times 10 to the minus 5, 2.2 times 10 to the minus 5 reciprocal seconds, if you wish. What's the concentration after 2 hours? SO2Cl2 final at time equal 2 hours. Okay. Now here we have a rate constant given in seconds and an expression and a question given in hours. Now you can want to do one of two things. You can convert your time to seconds or your seconds to hours. I prefer to go hours to seconds because you simply have to go 3,600 seconds per 1 hour. That cancels out, and you have 7,200 seconds, and we'll use that in our first order expression, first order decay expression. So they want to know the final concentration after 2 hours or 3,600 seconds, given the K value of 2.2 times 10 to the minus 5. Well, A equals A sub O E to the minus KT. So essentially, you're trying to find out what that final concentration is, A. And so we substitute the initial concentration, which is 0.0248 molar, and E to the minus. Now, I suggest you bracket this and do what's in brackets first, and then take the negative and then your exponential negative value. So your K value is 2.2 times 10 to the minus 5. Now seconds will cancel out because it's reciprocal seconds against seconds, times 3,600, and that bracket's like that. This is called the concentration correction factor. Because what it does is it reduces the initial concentration to whatever that concentration is on your decay curve. And so 0.0792 if you want to try. So when you make this calculation, you get this value, e to the minus 2.2 times 10 to the minus 5 times 3600. You'll get 0.924. So 0.924 of the 0.0248 is what's left, the remaining amount. So that is 0.023, 0.023 molar remaining. Now, the calculation tells you what's remaining, not how much has been consumed. Listen, please note that. How much is remaining, not how much is consumed. Some problems will come to you that will give you how much has been consumed, and then, but you'll have to turn that into a remaining amount. 60% has been consumed. Well, what's remaining? 40%. So you use 40% in your calculation. So you want to keep that in mind as we go forward in some of these, okay? There you go. Was given 2 hours, okay? So when we use the expression, the K expression here, time and the K value have to be in the same units, same dimensions. So we were given 2 hours, so I multiplied by 3,600 seconds per hour, 60 times 60. Okay, times 2, and that gives you 7,200 seconds. So when I work the problem, I put, oh, did I put 3,600 in there? Okay, should have been 7,200. Thank you, sir. I think that's what you were fixing to point at. Okay, yeah. So it would be 7,200 right there. Sorry about that. And so that would, problem math was right, but the entry was wrong. Okay, 7,200 then. Okay, so we make a correction and move on. So we need to find it at 256 seconds. Well, what this is giving you here is it's giving you information on where it is at 155 seconds, and we can use that to get the K value, because you're going to have the K value to actually calculate the concentration at 256 seconds. So A equals A naught E to the minus KT, and so we need to get the K value. Well, it turns out that K, let's see where we are, is equal to ln of A over A naught over the time minus, like that. It works out to that. You can solve this for this. You take the logarithm of both sides, move this A naught over to the left, and you come up with this K value, K expression. And so K now is ln of initial, which is 0.00100, divided by A naught, A final, it should be on the bottom, 0.00100 and 0.0067. Polarities are canceled, divided by a minus 155 seconds. And so whatever that comes out. So that now we can use that K value in the expression here and solve for 256. We still can use the initial concentration, 0.001, and then get the concentration at 256 seconds using the same expression. So now we go to the concentration at 256 seconds. So A equals A naught E to the minus KT. A naught 0.00100 molar. E to the minus K, which is 0.0026, and I need to compress 0.0026 times 256 seconds. The seconds will cancel out, and this will reduce that to whatever value we need. So 256 that, and second e to the x. So now that's 0.00100 molar times 0.5161. So that is this reduction factor right there. And so that gives me an exponential of 145.2 times 10 to the minus 4 molar after 256 seconds. There. Okay, so here's the chrome thiocyanate reaction, taking the chrome thiocyanate complex. K value is 2 times 10 to the minus 6. It wants to know what the first half-life is, and then how much remains, how many hours does it take for 25% remaining, or 12.5 or 6.25% remaining. Now, we can calculate the first half-life very simply in terms of the half-life equation. 0.693 over the K value, because KT was 0.693, and so 0.693 over 2 times 10 to the minus 6, and that's going to come out in seconds. So that's 3.5 times 10 to the 5th seconds is the half-life. All right, using the standard decay curve, time against concentration, what do we know about half-life? Well, if this is the initial concentration, this is where it's reduced to 50% remaining. So I'm just going to put 50% right here. If I cut that in half, that's 25% remaining. If I cut that in half, that's 12.5% remaining. If I cut that in half, it's 6.25% remaining in there. Now, the second thing is that this half-life time, the first half-life, right here, is 3.5 times 10 to the 5th seconds, okay? But it's also for the second half-life. So if we come over here and then come straight down to here, this gives you the second half-life. That's the first one. But this distance between the first and the second half-life is also 3.5 times 10 to the 5th seconds. And then this one is also the same number. Now this is true only for first order decay. So it's just a matter of recognizing that and adding, well, the first two to get to 50%, to 25%, and then 3 half-lives to get to 12.5, and 4 half-lives, of course, to get to 6.25. And so forth, like that. And so, 3.5, 10 to the 5th seconds. So this is T4 out here on the end. So the answer to the first one would be 2 times 3.5 times 10 to the 5th seconds. This one would be 3 times 3.5 times 10 to the 5th seconds. And of course this one would be 4 times 3.5 times 10 to the 5th seconds, like that. So in first order decay, the rate half-life is constant, so you can calculate however much remains proportionally, like that. So K value 0.693 over the half-life would of course be 0.693 divided by 4.46 times 10 to the ninth, and that will come out in reciprocal years. I got 1.56 times 10 to the minus 10 in years. So we need to get the time from the A equals A naught e to the minus kt. It can be shown that the time is equal to, of decay, is ln over A sub O divided by a minus k, like that. So we can use that expression to calculate the time it takes to reach 9% decay. Now, when you apply this is the important thing I was saying earlier in the lectures, that what you apply to this equation is what remains, not how much is decayed. So the problem specified, well, how long to 90% decay? Well, that would simply mean that 10% remains from the 100%, or 0.1, ln of 0.1 would go in here, and then divided by your k value. So that would be ln of initial over final. So ln would be 90%. 100 minus 90%, or 0.1, so that ln 0.10 divided by a minus 1.56 times 10 to the minus 10, and it'll come out in years. And so that works out to be, I get 1.5 times 10 to the 10th years. Quite a few days. Convert that to seconds, I think you'd have a big number. Anyway,